Hello everyone, and welcome to my talk on equivalence of hidden Markov models with continuous observations. This is a paper done in collaboration with Stefan Kiefer at the University of Oxford. Markov models are a type of verification model, I guess, that are used in, and also a machine learning model that are used in handwriting recognition and speech recognition, and from the verification side, in terms of modeling some kinds of protocols on the internet. But what exactly are they? In the finite case, they consist of some states. So in this case, we've got a yellow and a blue state, and some transitions. And so the top transition is labeled 1A, which means that there's a probability of 1 of transitioning from blue to yellow and emitting an A. And further down, we've got half probability of moving from yellow to blue and emitting a B, and similarly with the half transition for an A at the bottom. And so this HMM, as they're known, produces an infinite word, so an infinite sequence of letters, depending on the initial state. But the sequence of word is also probabilistic. So it gives rise to a probability space, and importantly, generate some events which have different probabilities associated with them. So some examples are the first three emitted letters are A, A, B. So just to run you guys through that. So from the blue state, we can emit an A, and then an A with half probability, and then we can't emit a B, so this event would have probability 0 if we started from the blue state. And from the yellow state, we would have a half probability of emitting an A, then 1 probability of emitting an A again, and then finally half probability of emitting a B. So that event would have probability a quarter if we started from the yellow state. So different events, so the probabilistic system is dependent on the initial distribution of the system as well. So the reason why we're interested in equivalence is because sometimes the initial distributions can behave identically, and we are interested in whether or not we can compute whether two initial distributions do behave equivalently. So this is a sort of slightly straightforward example where we've got two states, and because the outgoing transitions from both states are identical, all the runs from this system, regardless of the initial distribution, will behave exactly the same way. So let's develop some more terminology about events. So they're sets of infinite strings. Here's sort of some examples. So these give rise to cylinder sets. For example, first letter is an A, first letter is a B, etc. Some different examples. We can have first letter is an A and second letter is a B, and that would be written down in this way in the bottom left. So AB, and then there's sigma with an omega on the top right is meant to mean the set of all infinite words. And then we can talk about unions of these cylinder sets as well. So we've got AAB and then all words, and ABB. So what we are primarily interested in is when the transitions emit from a continuous distribution. So in this example here, instead of emitting letters from a finite set, say AB, we're emitting from the interval 0 to infinity, and in this case exponential distributions. So in the top left we've got an exponential distribution with rate 1, and in the bottom we've got an exponential distribution with rate 2. And I know that the diagrams look very similar, but if you look at the point half half, you'll see that in one of them it's below the line, and one of them it's above the line. So they are in fact different distributions. And these halves here are meant to represent the probability of emitting from that particular distribution. So this system is producing a sequence of non-negative real numbers, and therefore generates an infinite word consisting of non-negative real numbers. We can similarly talk about events in this case, but you'll notice that any finite word produced by the system has probability 0 because they're continuous distributions. So instead we have to talk about cylinder sets in a slightly different way. A classic event would be, for example, the first letter is in the interval 0, 1, and you can sort of work out what the probability is of that happening depending on the initial state. And I think it should be fairly clear that it would be different depending on the initial state in this example. So what I've done here is I've taken out the graphs on the picture in the top right and just replaced them with the equations and kind of moved the probabilities into the equation as well. So some simple examples of events are, as before, first letter is in the interval 0, 1, and similarly, first letter is 0, 1, second letter is in the set 2 to E. And we can write these like this. So once again, this sigma omega is the set of all words. Right, so let's develop some notation now. In the top left, we've got some matrices. This psi is what we call an observational density matrix. So it takes a letter that's being produced, and this is in the finite case, by the way. It takes a letter that's being produced and gives you all the transitions that produce that letter. So in this example, we're transitioning from the yellow state, which is considered state 1 in this matrix ordering, with for the letter A with half probability, like this, and then with B, we've got this B transition as well from yellow to blue. In the bottom left, I've written sigma to indicate the particular alphabet or observation set that we are working with. So in the finite case, it's just A, B, but in the exponential case, which we saw before, it would be the interval from 0 to infinity. And on the right, we also discuss initial distributions, because this is important, as we said before, about the actual distribution of words depends on the initial distribution. So we write these as row vectors. So pi1 would be a vector which represents the probability of starting with probability 1 from the yellow state, and similarly with pi2 in the blue state. And this leads to quite a natural way to describe the probability of the cylinder sets. So in the case of the first three letters being A, A, B, and then anything allowed afterwards, we can write this as a matrix product where we look at the transitions that are associated with each of those letters and kind of build up a matrix product where we start from the initial distribution and then sort of calculate the probability of taking each of the paths associated with those letters. And this 1t is a 1 vector at the end, because if you just look at pi1 and multiply it by all these matrices, you get the state distribution having produced that particular word. So we sum over all the possible states. So let's go back to equivalence. In the finite state case, this is actually a solved problem. So determining whether two initial distributions are equivalent goes back to 1992. And just quickly remind you that we say that two initial distributions are equivalent if and only if the distribution on the infinite words is the same. So yeah, it's a solved problem. It used to be in quartic time, and then it was reduced 9 years ago to cubic time. But no one's really studied the continuous case, and certainly no prior algorithm exists. And I think something that a lot of people might be thinking is like, well, how do you even encode the continuous functions? And so what our work is, sort of half of our work is based around this kind of encoding scheme, and then half of it is how to go from the encoding scheme to this algorithm. So what we've done is we've done a reduction based on an encoding from this continuous case to a finite case. And we've restricted ourselves slightly to exponential, normal, and polynomial distributions, and convex combinations of these distributions. But that kind of encapsulates a lot of use cases. So I think we're fairly happy with the breadth of that particular work. And importantly, the encoding that we've chosen is based around the actual important information that is needed to produce the reduction from the continuous case to the finite case. So exponentials are encoded as just their means, because that's, it turns out, is the only important information. Normals as pair of mean and variance. And then we also got these sort of slightly weird polynomial distributions, which includes uniform distributions, but also includes stuff like linear distributions on a particular interval. And in general, they're kind of like sums of interval indicator functions and some power of x would form, and a coefficient, sorry, would form the basis of these kind of polynomial distributions. And they're encoded as coefficient and interval supports. And our algorithm is polynomial in the size of the encoding. So this is, I think me and, so we would like to perhaps just clear up that although our work we've proven for exponential normal in these polynomial distributions, there is sort of a wider use case that sort of depends on the particular functions that you're working with, but you can kind of it doesn't have to just be restricted to these. So it is possible to develop it. We've just happened to chosen these as a sort of starting point. All right. So how would someone do a reduction from a continuous emitting chain to a finite emitting chain? One way you might want to do that would be just to give every PDF in your continuous chain a letter, and then look at the chain produced with those letters and ask the question, well, are the states equivalent in this chain? And it turns out to not quite encapsulate all the information you need. So here is a sort of example of why that's the case. So here in the top of this chain, we've got some linear distributions, which I kind of described before. So hopefully that clears that bit up now. We've got a sort of slanting down distribution and a slanting up distribution. And if you sum these distributions together, you actually get this uniform distribution, which is at the bottom. And because these distributions here, the ones from 1 to 2, are all the same, the behavior you see is actually that from either blue or yellow state, you produce a number uniformly, and then you start producing, you produce a number uniformly from 0 to 1, and then after the first letter is emitted, you constantly produce letters uniformly from 1 to 2. Numbers from 1 to 2, sorry. So a typical run might look like 0.6, and then 1.3, 1.7, 1.9, etc. And because of this kind of like summing of the distributions, we get that the yellow and blue states are equivalent. But under the labeling scheme that we described before, that would not be the case because these distributions are, fundamentally different. So we need a slightly different approach. The fact that we had to sum two distributions together to kind of get the same behavior as another distribution led us to think about the linear independence of functions, the linear independence of the emission functions, the PDFs. So here's a sort of quick definition for those that aren't super aware. So we say a set of functions is linearly independent if there is some set of numbers that produces a zero function when we sum them with the coefficients together. Hopefully this definition on the screen is a bit clearer than my verbal definition. And we say a set is linearly dependent if it's not linearly independent. Some examples of linearly independent versus dependent functions are cos squared, sine squared, and 1. This is dependent due to the trigonometric identity. And then linear independence of polynomials comes from something, there's a particular type of, well, one way to prove it would be to look at something called a van der Monde matrix and show that the van der Monde matrix has full rank. So how do we go about performing this task? What I've done is I've written out these functions as delta. So the delta is meant to be an identity function. So this is a uniform distribution. This is our slanting up function here, and this is our slanting down function, and this is our sort of finishing function, which sort of signals the end of the behavior of the chain. And we said before there was a linear dependence given by the uniform distribution as the sum of these two distributions. So what we can kind of do is I've started in the top left, and the way this sort of algorithm is going to work is it's going to say, well, there's a linear dependence here between the uniform distribution and the slanting up and slanting down distributions. What I'm going to do is I'm going to sort of split off this transition into the two transitions given by the linear dependence. So this is what this kind of transformation is showing, is that we're going to split this uniform into a slanting down and the sum of a slanting down and a slanting up, and then perform the labeling reduction on this chain, which now has all of its functions being linearly independent, and producing this finite alphabet chain on the right. And it turns out that this kind of strategy gives you an if and only if relationship between equivalence of initial distributions. Right, so let's. I'm going to try and sort of give a bit more intuition about the particular notation I'm about to introduce. So just to clarify this again, so what we've done is we've taken this sort of split off. So I'm just going to take out the pictures for now and just give equations because it's a little easier to kind of compress things on the page. So I've just copied across onto some equations, and then what we're going to do is we're going to write this chain as kind of the sum, in inverted commas, of these transition chains. So on the left here we've got our slanting up distribution, which is just the normal x. Slanting down is 1 minus x, and the uniform is because we've written the uniform 0, 1 as the sum of these two distributions, that kind of splits off into the first two, and then the finishing distribution is the indicator from 1 to 2. So we've kind of split off this HMM into 3 different parts, where each of the functions in those different parts is linearly independent. And one way to write this would be to in this way. So in this equation, we've got our original observational density matrix on the left, and we've got a sum of fk, which are independent functions that depend on x. So this is our alphabet. So it's a, b in the finite case, and 0 to infinity in the infinite case. And pk, which are matrices, and these are kind of talking about the transitions that are associated with those PDFs. And one thing that we have to we sort of set is that the fk have to integrate to 1, so they have to be actual probability density functions. And you can imagine just changing the values in the pk so that is the case. So you can just kind of multiply all the values by a scalar in the pk so that the fk always integrate to 1. Actually just going back, one thing that, so the way this reduction technique is going to work is, what we're going to do is we're going to take our observational density matrix, or rather the encoding of our observational density matrix, and we are going to work out what these pk need to be, and our sort of system gives a polynomial time algorithm to do it. And under some cases, what you could do is just take the pk and make that your new set of matrices in the finite case. So if we go all the way back, you'll see we have these psi A and psi B for the finite case, where we just have straight set of matrices. So imagine that instead of A and B, we sort of give each of the different independent functions a letter from 1 to n, if there are n independent functions. And then these matrices here are what gets plugged into the finite case, and we run the equivalence checking algorithm on that finite chain. But there is a slight problem with this, in that, and I'll explain it by this example here. So in this chain here, we've got 4 states. We've got a finishing distribution, which is uniform from -1 to 0. And we've got some other uniform distributions from 1 to 2 and 0 to 1, and this is 0.5 to 1.5, and this is a disjoint uniform distribution from 0.5 and then also from 1.5 to 2. And yes, so you'll notice that the sort of left distributions here sum together to give the same thing as the right distribution. So there is a linear dependence here, and I've given that at the bottom. But in this linear dependence, there's a negative sign, which means that you can't, when you sort of do this linear decomposition, and the entries in the matrices aren't too important, but you'll notice that in one of the dependencies, there's a negative sign. And that's true actually in this example of if you picked any 3 of the functions and chose those to be your independent functions, you'd have to write the last function with a negative sign as part of the linear dependence. So it's a slight problem. So instead what we do, so that the coefficients might be negative. That's the sort of problem in the determining the linear dependence. So instead what we do is we compute an alpha such that this matrix here, P, which is the sum of all the matrices minus alpha pk, is non-negative. And we can actually always do this. And the finite chain that preserves equivalence from the continuous chain looks like this. So these are individual. So we sort of invent letters for each of the independent functions. And then each of these matrices are associated with those letters in the finite chain. And it turns out that this chain preserves equivalence with the continuous case. And I've also given the alpha at the top that you need to compute. So it's just based on the value of P and some values of the pk as well. So I think you'll notice that we didn't actually discuss anything about exponential, normal, or these polynomial functions, and that's because part of our work is we showed that in those kind of cases, basically if say you were to take a space of normal distributions and exponential distributions, you'd automatically have linear independence if the rates of the exponential distributions are different and if the means and variances of the normal distributions are different. And then just determining whether working out a basis for the polynomial distributions is as simple as kind of like putting them in a matrix and then putting the sort of coefficients of the polynomial distributions in a big matrix and working out a basis of that matrix space. So that part of the work is kind of slightly more straightforward, but the sort of fundamental result is actually more general in terms of kind of taking any functions which are linear independent or which you can compute whether or not the functions are linear independent, and will lead you to this kind of reduction technique. So thank you very much for listening to my talk. I hope it was informative, and yeah, thank you very much, and I think I'll probably take some questions now.